In Part 2 of Lecture 3, we will introduce the idea of the grammar. We have used the term syntax quite frequently, but it is not that formal. The proper and more formal term is grammar, for which we can provide a formal definition. A grammar is a four-tuple, consisting of four things. T, a set of terminals, basic symbols within the grammar of the language. N, a set of non-terminals, which are aggregates of symbols, which may include a mixture of terminals and other non-terminals. S, a start symbol, a special non-terminal that we use to refer to the whole program. And P, a set of productions, rules that tell us how we can combine terminals and non-terminals to form other non-terminals. To understand this, you need to see an example. If we were talking about a human language instead of Java or another programming language, we would start with a sentence, what we are usually looking to construct in English. That would be our start symbol. We know that this can be deconstructed into a noun phrase and a verb phrase. Yes, this is not the only way that we can deconstruct a sentence, but it is one legal way to do it. The noun phrase can be deconstructed into an article, a or the, and a noun. We see that the article can be deconstructed just as we said, and that we can do the same thing for noun. And then we can do this for verb phrase and verb as well. We already know that sentence is our start symbol. All the other terms that describe how we group words are also non-terminals. They appear in italics on the slide. And the word that we have in the actual sentence as we read it, a, the, girl, dog, sees, pets, these are the terminals, and they're indicated in boldface. We want to use these rules to produce the sentence, the girl sees a dog. We apply Rule 1 to get a noun phrase and a verb phrase. Applying Rule 2 gives us an article, noun, and verb phrase. Applying Rule 3 introduces our first terminal, the word the. Noun gets replaced with girl, applying Rule 4. Applying Rule 5 gives us the girl, followed by a verb and a noun phrase. Applying Rule 6 gives us the girl sees, then article and noun. Applying Rule 3 gives us the girl sees a noun, and applying Rule 4 gives us the sentence that we wanted. Programming languages need a grammar that is flexible enough to allow for the range of constructs that we need to write programs, but enough structure to make it possible and not too expensive to process the program. That typically requires context-free grammars. They are called context-free because the rules that allow us to break them down apply no matter where a given grammatical structure may appear. This is different from human languages, which are usually context-sensitive. How and where you apply certain rules to deconstruct a sentence will depend on the context in which you find it. In other words, the fact that you apply the rule in one case does not mean that you will necessarily apply it in a different case when using a context-sensitive grammar. But it's a different story in context-free grammars. Backus-Naur form, or BNF, allows us to specify the productions, or grammatical rules of a language, any language, whether it is English or Spanish or Fortran or Java. There are a few symbols that you need to know. The colon equals, or the right arrow, indicates that you can derive an expression for the non-terminal on the left-hand side using the right-hand side of the production. When we use the symbol, we say that the non-terminal derives whatever we have on the right-hand side. And then there is the vertical line. It separates two potential right-hand sides. We can substitute either of these two expressions for the non-terminals on the left. So our production becomes E derives E plus T, or it derives T. We can do the same thing with T derives T times F, or it derives F. The last production becomes F derives identifier, or it derives constant, or it derives an expression inside parentheses. We can use this rule however many times we want to generate one of an infinite number of possibilities. We can also use this to assemble a parse tree for a given expression. BNF allows us to put together a formal specification for the language that makes it fairly easy to see if a program in that language conforms to its requirements. When we parse the program, we will be doing the opposite of what we did before. Instead of substituting repeatedly to replace a non-terminal with a program, we will take our program and see what kind of syntactic structure will correspond to the program that we are analyzing. Syntax and semantics may come together, but they are not the same, and syntactic correctness does not always correlate with semantic correctness. I can write, "The girl ran home," and after I read it, I know that it makes sense. But reversing the nouns change everything. Even though it is nonsensical, obviously houses don't run, it is still syntactically correct. In programming languages, we have rules that we can use to determine if a program is correct semantically. Most of the time, it is just a matter of making sure that data types are used correctly. In human language, we almost always need to use knowledge from outside the sentence to check its semantics. Languages are sets of character strings of finite length that come from the language's alphabet. When we are looking at the syntax of a sentence or of a program, and not just on how to assemble individual words correctly, it is the words or tokens of a language that comprise an alphabet. If I am trying to parse a sentence in English, my alphabet is not A, B, C. It is comprised of every word in the English language, even though there are hundreds of thousands of words in English. The alphabet of a programming language is usually far more restricted. Most programming languages have fewer than 100 tokens. What you see here is a portion of a programming language's grammar. All we have here is the grammar for simple assignment statements. We can see clearly that an assignment statement is a variable name, an equal sign, serving as an assignment operator, and then an arithmetic expression. We then have rules showing how expressions are put together. An expression can be a single term, or an expression plus a term, or an expression minus a term. A term can be a simple primary, or a term times a primary, or a term divided by a primary. A primary can be a variable, or a literal number, or an expression in parentheses. A variable is an identifier, or an identifier followed by subscripts in square brackets, and I can specify a subscript list in the same way. This spells out exactly what an expression could have, but writing the grammar this way also codifies the fact that we do multiplication and division after what is in parentheses, and we do addition and subtraction after multiplication and division. If we want to generate strings that are legal in this language, we can use single replacement. In the example here, our start symbol derives an S in parentheses, which in turn derives two S's in parentheses, which then derives a pair of empty parentheses, and an S in parentheses, and then lastly, two empty pairs of parentheses in an outer set of parentheses. All we had to do was to apply these rules 4 times. The parse tree that you see in the slide is a graphical representation of the process of deriving the string in the previous slide based on the grammar specified in that slide. We can see here that the original S derives an S in parentheses, and that the S in parentheses derives two S's, each of which derives a pair of parentheses. The parse tree in the slide is for the English sentence, "The girl sees a dog." Following the rules of the grammar, we break the sentence down into a noun phrase and a verb phrase. The noun phrase gets broken down into an article, the word the, and a noun, the word girl. The verb phrase is broken down into a verb, the word sees, and a noun phrase, which is then broken down into an article, this time the word and another verb, the word dog. The same process is used to parse an assignment statement according to the productions that we saw before. The assignment statement is broken down into a variable, an assignment operator, the equal sign, and an arithmetic expression. The arithmetic expression is a single term, which consists of a term and a primary, an expression in parentheses. We can break down this parenthetic expression into an expression and a term, and these will break down into a variable each. This allows us to make sure that it is syntactically correct, and the syntax helps guide us toward making sense of its meaning.